Good morning, class. Today, we're going to learn the Fibonacci sequence. As you can see, I've written down the real numbers and I boxed the Fibonacci numbers. So this is how you get the Fibonacci numbers. It's 0, e plus 1 equals 1. Then you take the previous number, which is 1, so you take 1 plus 1 equals 2. Then 2 plus 1 equals 3. 3 plus 2 equals 5. And so on. Okay, next we go to the ratio. As you can see, 5 and 8 are Fibonacci numbers. If you round them out, it becomes approximately 0.618034. It's the same for other Fibonacci numbers as well. To make things simpler, I have done a stairway to Fibonacci. So here is how it goes. Since you need two numbers to get a Fibonacci number, let's take 0 and 1. So 0 plus 1 is 1. Then you take the previous number, which was 1. So 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21. 21 plus 13 is 34. And then you continue until you reach infinity. And that's where you find Fibonacci. Now we're going to watch a video of the Fibonacci sequence.
Fibonacci's full name was Leonardo of Pisa or Leonardo Pisano. Sometimes he used his nickname Bigelow, which meant good for nothing or traveler. He was born in 1175 in a place called Pisa in Italy. His father, Guglielmo, a merchant, traded in Bugia. During his journey with his father in North Africa, Fibonacci gained a lot of valuable mathematical systems that were popularly used in the countries they visited. After 15 years, he ended his long travel and returned to his hometown, where he began writing books based on his foundation of mathematics. The copies of Fibonacci's handwritten books that we fortunately have are Liber Abaci, Patrica Geometrica, Flos, and Liber Quadratotum. In Liber Abaci, the Fibonacci numbers were first introduced. It became one of the reasons why Fibonacci is best remembered today.
Okay, so today I'll be talking about Pascal's triangle and how it relates to the Fibonacci sequence. Alright, so how the Pascal's triangle works is this. You start with number 1 and you bring down that number all the way on the left and all the way on the right. And then you just bring down the number 1 here, you get 1 and 1, and you plus these two together and you get 2. So the entire triangle works on that basis. 1 plus 2, 3, then 1 plus 3, 4, 1 plus 4, 5. And if you notice, you will see this pattern. The counting numbers work on this step. 1, 2, 3, 4, 5, 6, all the way on, and then on this side also. Besides that, we also look at this step. 1, 3, 6, 10, 15, 21, 28, 26, and 45, and on so. Right, if I took the 1 and I plus 2 to it, I will get 3. If I took the 3 and I plus 3 to it, I'll get 6. So it's just basically, the numbers are going on and on, plus 2, plus 3, plus 4, plus 5, and it goes on and on like that. Now, how it relates to the Fibonacci sequence is like this. I take the number 1 here, and then I also take this number 1 here, and then from here onwards I can take this, the 1 here and the 1 here, and I'll get a 2. Then I'll take the number 1 here, 2 here, and I get number 3. Then go on, 1, 3, and 1, I'll get 5. I go on again, 1, 4, 3, I get 8. Then I go on and on again, 1, 5, 6, 1, I get 13. So these are the basic numbers of the Fibonacci sequence, and as I go lower and lower, the value will increase based on the Fibonacci sequence. And besides that, the interesting part about Pascal's triangle is it also has this. 1, 2, 4, 8, 16, 32, and on so. So these numbers are basically the multiple of 2, multiple of 2, multiple of 2, and I get the value underneath it.
Today I'll be talking to you about the golden ratio and how it relates to the Fibonacci sequence. The golden ratio is also called the golden mean, the divine proportion, or it's also called golden section. Okay. The golden ratio is a number of 1.618. It starts with 1.618. It's a never-ending number, sort of like pi. The golden ratio is also known as, it's actually known as phi. This is phi, or you could draw it like this. I'll tell you how it relates to the Fibonacci sequence. So I wrote some of it down. It's actually a really long sequence, so I just stopped until 55. Now, it's A over B, A being the right number, like this is on the right, let's say this is on the right, and B being on the left. Or this would be on the right, and this would be on the left. So yeah, it's like that. Okay, let's take 13 over 8 as an example. 13 over 8 is 1.625. Let's take another example. 21 over 13. Okay. 21 over 13. That gives you 1.615. Let's take another one, something slightly to this side. 5 over 3. That gives you 1.67. Yeah, 1.67. So what if you try all of them out, the further you go, the more accurate it gets. As you can see here, it's all really close to 1.618.
The Fibonacci sequence can be seen in many instances in nature, such as in the reproduction of rabbits as well as honeybees. When a female honeybee lays an egg and it is unfertilized, a male will hatch. Therefore, each male only has one parent. If the egg is fertilized, a female will hatch. Therefore, each female has two parents. So, for instance, if we start the first generation with a male honeybee, we will have 1. In the generation above him, he has one parent, that is a female, as evidenced by here. So in this generation, there is also 1. In the generation above that female, we have 2. This is because each female has one female parent and one male parent. This pattern continues also in the third generation. The female parent will have 2 parents while the male only has 1. Therefore, in this generation, there are 3. If we do this pattern for the additional generation, we will get 5 parents. If this is continued for another generation, there will be 8 parents. Do you see where I'm going here? Each of these numbers are consequential Fibonacci numbers. Upon closer inspection, it is quite obvious that the Fibonacci sequence occurs a lot in nature. This is especially evident in flowers, vegetables, shells, and even humans.
You can see that the Fibonacci sequence appears nearly everywhere in nature. You can see it in petals on the flowers, pine cones, pineapples, cells, and more. It's a nature way of numbering things. So, are you listening to me?
Yeah.
I get it now.